Hello everyone, and welcome back to Mitchell's Physics Review. Today we will be working on Gauss's law. Let's take a look at our problem. A solid sphere of radius 40 centimeters has a total positive charge of 24.9 microcoulombs uniformly distributed throughout its volume. Calculate the magnitude of the electric field at the following distances. Let's start by taking a look at our picture. As we can see, the darker blue circle is representative of our first sphere with the radius of 40 centimeters. Since our object is a sphere, our Gaussian object is also going to be a sphere, and we're going to say it's of radius r. Now let's take a look at our givens. We're given that A, or the radius of the dark blue sphere, is 0.4 meters, and that the charge is 24.9 times 10 to the negative 6 microcoulombs. Now here's where it can get a little bit tricky. We're going to start by looking at part A, 0 centimeters from the center of the sphere. Well, to do this, we're going to have to start by deriving an equation for the electric field. So, we're going to use Gauss's law that the electric field times the area of the object equals the charge enclosed within the object over epsilon naught. However, as you're going to notice, we don't know either the field or the enclosed charge, so we're going to have to find a way to plug in for one of those, which is where we come to rho equals Q enclosed over V enclosed, also known as the charge over the volume equals the enclosed charge over the enclosed volume. From there, since we're looking for Q enclosed, we're going to rewrite the equation and isolate charge enclosed to get the charge times the volume enclosed times V. Now in this case, our volume enclosed is 4/3 pi r cubed. Why is that? Because inside of the sphere, our Gaussian surface is this smaller sphere, enclosed, for example, and it has radius r, which is why you'll notice up here it is r cubed and down here it is a cubed, because the volume of the total is this bigger, darker blue sphere with the radius of 40 centimeters. From there, we're able to cancel out 4/3 and pi to get Q enclosed equals charge times r cubed over a cubed. Now, we can take this and plug this back into our equation. We can also substitute in the area of a sphere, which is 4 pi r squared. So now we get down to this line. E times the area, 4 pi r squared, is equal to the charge, r cubed, over epsilon naught times a cubed. From there, we can divide to get electric field alone. Then, we get electric field is equal to charge times r cubed over a cubed times r squared, and we're going to separate this piece 1 over 4 pi epsilon naught. We're going to do this so that we can simplify, because from our equation sheet, we know that 1 over 4 pi epsilon naught is equal to the constant Ke. We can also reduce the r variable in this equation. So we get down to this line where the electric field is equal to the charge times the radius times Ke over a cubed. Now that we have derived an equation, we can start solving A through C. So now with our derived equation, we can find the magnitude of the electric field 0 centimeters from the center of the sphere. This is our easiest problem because we're going to use our equation, and instead of plugging in all the numbers, we know if we just plug in 0 for r, it's going to equal 0 kilonewtons per coulomb. Now, let's take a look at part B. Calculate the magnitude of the electric field 10 centimeters from the center of the sphere. We're going to want to start by converting 10 centimeters into meters, so r is equal to 0.1 meter. We're then going to use a derived equation and plug in all of our givens and our new given of r equals 0.1. And for Ke, we have 9 times 10 to the 9th, the given charge of 24.9 times 10 to the negative 6. Our given value of r, 0.1, and A, the radius of the initial sphere, 0.4. From there, we can plug it into our calculator to get 3.5 times 10 to the 5th. However, this is in newtons per coulomb, so we're going to convert by dividing by 1,000, so we can get that it equals to 350 kilonewtons per coulomb. Now, let's take a look at part C. Calculate the magnitude of the electric field 40 centimeters from the center of the sphere. For part C, it will be very similar to part B. We're going to convert R into meters, so R equals 0.4 meters. Once again, use our derived equation. Plug in the same constant, 9 times 10 to the 9th. We're going to plug in the same charge, 24.9 times 10 to the negative 6. This time with the new value for R, 0.4, all over A, which is still 0.4 cubed. From there, we get 1.4 times 10 to the 6, and to convert to kilonewtons, we're going to divide by 1,000 to get 1,400 kilonewtons per coulomb. Now, let's take a look at part D. Find the magnitude of the electric field, 67.5 centimeters from the center of the sphere. If you notice something a little off about this is because the radius of our sphere is only 40 centimeters, which means the point charge is outside of the sphere, meaning it is not an enclosed charge. As a result, we're going to use the equation of an electric field for a point charge. Let's start as we did before by converting R into meters. So R equals 0.675 meters. Now we're going to use the aforementioned equation, E equals KE times Q over R squared. From there, we plug in the constant, plug in our given charge, and plug in the given radius to get 4.92 times 10 to the 5th. We're once again going to divide by 1,000 to get to kilonewtons, and we will come out with 492 kilonewtons per coulomb. The overall hardest part of this problem for me was deriving this equation, especially when it came to using rho equals Q enclosed over V enclosed to find one of the unknowns that we could substitute in. What I really learned from this is when we're looking at equations that have to do with electric field area and encharged closes, it's best to start by drawing the picture to see what charges will be enclosed, which ones aren't, and which ones might be right along the edge. It'll help out a lot more. I hope you learned a lot from this video, as did I. Have a great day.